So, good morning, good afternoon, everyone, and welcome to this webinar of WFEO Committee on Energy and World Energy Council France. For those who don't know me, my name is Vaiani. I'm the Secretary General of the World Energy Council France, which is the French member committee of the World Energy Council. And I also have the honor of chairing the Energy Committee of the World Federation of Engineering Organization. For those who may not know yet be familiar with WFEO, Chloe, if you can just skip this slide. The World Federation of Engineering Organization is a global non-governmental organization that represents the engineering profession worldwide. It is established under the auspices of UNESCO, and it brings together the network of 30 million engineers across more than 100 countries, and with them a large and very valuable pool of expertise. WFEO operates through 13 specialized committees and working groups, and you can see them on the PowerPoint here. What are we doing as a global engineering federation to advance the SDG 7, clean and affordable energy for all through engineering? As energy engineers and scientists, we all share a responsibility to identify and implement the most effective technologies for sustainable development. And as chair of the Energy Committee, I strongly believe that international cooperation and sharing of knowledge, including best practices, efficient energy policies, and technological innovation are key to achieve SDG 7, affordable and clean energy for all. And this is clearly the guiding principle of our work within WFEO and within the Energy Committee. And among our initiatives, we have launched our 2025 webinar series. Chloe, if you can just skip the next one, please. Which started with electrification, access gap, and policy recommendation to address it, with Professor Abubakar Sambo, chair of the Electrification Task Group of WFEO. Then we shift with a focus to understand why nuclear power is making a comeback, with Dr. Henri Payer, Head of Planning and Economic Studies at the International Atomic Energy Agency. And then we explore the topic of PV module recycling as a necessity for future PV development with the Committee on Energy Solar Task Group Chair, and with experts and industrial from different regions of the world. And today I have the pleasure to shift to another key dimension of the energy transition worldwide, artificial intelligence for power system. And I'm very happy to give the floor to this morning and this afternoon for you to Dr. Yishen Wang, which is expert from the Department of Artificial Intelligence at China Electric Power Research, who will give us an overview on how these important topics is managed in China, which is a really important way to share expertise and knowledge. Dr. Yang, please, I give you the floor.
Oh, thank you very much, Marilyn, for the introduction, and thank you very much for the WFEO for the invitation. It's really my pleasure to introduce some of our work on this topic. So can you all see the slides? Okay, so the topic for today is the AI for power system application and perspectives. So I'm from the Department of Artificial Intelligence from the China Electric Power Research Institute. For those of you who are not familiar with our institute, so actually we are the R&D research center for the SGCC, which is the State-Grade Corporation of China, the largest utility company in Asia. And so here we are trying to, in this seminar, talk about some of our AI applications that the work we have done, and also some of the perspective that we look for the future, because right now we know that AI is, growing very fast, and we know that the technology will not stop at some certain point. So we have to have some, the future perspective, and some of our perspective are also be covered in today's seminar. So in today, I will basically talk about like four parts. First, we'll give a very brief overview for some challenges we are facing in the current power system. And then we'll talk about some of our SGCC's AI Plus action plans. So what is our strategics in this area? And then we are talking about some typical applications in the asset management and in the grid operation, as well as in some customer services. Then at the last part, I will talk about some of our perspective for the AI for science, which is a really hot topic since recent 3 or 4 years. We'll show some of our results and our work on this topic. Hopefully, and this will be useful and will be to you guys. So for right now, so actually China is developing the concept of the new power systems. Basically, we are trying to meet the dual carbon target, which is like we will achieve the carbon peak in the 2030 and achieve the carbon neutrality in 2060. So this is actually a very challenging topic. But the thing is that we have to understand, acknowledge that the power system we are trying to build and develop is actually the largest and most complex man-made system in the world. So for example, right now, when we are trying to projecting the power system in 2030, like in the SGCC area, we will achieve, install the capacity of renewable energies, to exceed more than 3 billion kilowatts. And also we will almost have like more than 40 UHVDC projects. So that will make the whole system to be very challenging. At the same time, we'll have some, additional challenges we are trying to cope with. Is this renewable energy. So we have to handle the uncertainty in the system. So we have this renewable energy penetrated, but we know that it's not only in the centralized way. There are also many, the PV solars, some like distributed wind farms. They are from the distributed side. So we have to handle the uncertainty from the centralized farms and from the distributed manners. At the same time, that actually is from the source side. From the low side, we also have additional and a lot of uncertainties. We have a lot of EVs, so those EV integration will have this by two-way interlinks, as well as we also have the microgrids. We also have some flexible loads. So all these coupled uncertainty from the source side, from the low side, will make the overall forecasting and operation optimization more challenging. At the same time, the system is becoming more and more openness. Like the system, keep growing, and there's a keep changing the system. There's always a dynamic changing. So we also have to consider how do we handle this openness issue. And it's, at the same time, we know that right now we have more and more extreme events. There are some climate issues. So we have to consider how do we, make sure the system is more resilient and robust when we coping with these vulnerability issues. So overall speaking, when we developing this power system, we make sure we want to have the better forecasting and better simulation analysis, as well as the operational optimization. But these three important tasks are actually becoming more and more difficult. And right now, actually, with the innovation and development from the AI, artificial intelligence, actually they can improve the productivity of the system quite well. So basically, it can serve as this intelligent engine for these new power systems. So, but AI right now we know that it's a game-changing tool. So the ultimate goal is to still serve the grid, to make sure our grid business they are running better. We have better grid operation. We have better asset management. So they are still need to serve the target. So we want the AI, to enhance our capabilities in this source load forecasting, in this analysis as well as the optimization to make better decisions. So ultimately, we hope during the process of the evolution, we want to making the overall operation mode, towards more like autonomous learning, automatic computation, as well as the intelligent decision making. But this will, have to handle, some important issue like how do we make sure the forecasting is more accurate. So to achieve this high precision forecasting, also when we have to run a lot of analysis, we make sure this, when especially a lot of power electronic devices is integrated, how do we handle this high order system dynamics? How do we run better and faster simulations? And then when we talk about the operational optimization, so we have this multi-objective. We want to achieve, uh, the more and more renewable integration. We want the system to be more and more economic, but also we need to ensure the system is reliable and secure enough. So we need to have make the decisions, consider this multi-objective and a lot of operational constraints. So we hope using this AI can serve as this intelligent engine and to help us address this issue. But to talk about these three important tasks, so we have to also understand that there are a lot of challenges when we're using AI. So for the energy forecasting, so we know that the forecasting techniques has been developed a lot from a long time, but still we cannot say any forecasting method is perfect. There are always some errors. So when we run the system, we have to consider how do we better run the system, considering we know that there's always error. So, and also we have to originally most the forecasting is from the high voltage side, from these more aggregate levels. But right now it's more and more distributed renewables in the system. So we have to, run better forecasting from the low voltage level, and also consider some, and also like for the climate and climate change, some extreme events. So for some of the issue, so we have to consider to do this low sample and small sample forecasting, and to make sure overall, to make sure the energy forecasting we are handling is to achieve the multi-time scale and high reliability predictions. And for the simulation analysis, the system, because we have a lot of dynamics, we have a lot of the power electronics. Actually, the system, this nonlinear characteristic is becoming more and more obvious. So the original and classic conventional methods, they are facing some like computational bottlenecks. So when we have to consider these large systems, we want to know that how can we better achieve the timeliness and precision in these overall simulation tasks. And then we have the topic for this operational optimization. So we have a lot of like distributed energy resources. We have more flexible loads. So and already at the same time we have a lot of new and distributed energies. So basically the overall decision space dimensionality is becoming more and more, it's becoming larger and larger. So we like call it like explosive growth. So originally we have some like classic optimization solvers, like, but how can we handle this new like optimization problem like mathematically, to be more computationally efficient, especially we want to overcome the trilemma between the computational efficiency, computational accuracy, and the computational scale. And those are the topics that we hope AI can give us some answers. And very interestingly, we know that recently this year, the Nobel Prize in Physics was awarded for the achievement from the quantum computing. But last year, actually, both the Nobel Prize in Physics and in Chemistry was awarded to AI. So that's very interesting. Like for example, the Nobel Prize in Chemistry, like last year, was awarded to DeepMind for their contributions of the AlphaFold, which is a protein structure prediction. So which is a very typical example that how AI can reshape and make a like profound impact in this chemistry and biochemical like field. So they can find better protein structures. And interestingly, and this is a very typical like AI for science example. And interestingly, for the last year's Nobel Prize in Physics, was awarded to Geoffrey Hinton and John Hopfield for their foundational discoveries and the invention within. Basically, they brought and they are inspired from the physics to develop better AI structures. So this is not only like AI for science, but more like example of science for AI. So we can see that both the link between the AI and the science are very tight and very coupled. So this actually give us a motivation that because actually, our power system and energy field are developed and derived from the physics. So the AI and the power system and energy systems, actually, they are also interlinked quite tight to each other. We hope that with these AI tools, we can have better AI for power system examples. And at the same time, these examples will motivate inversely to develop our better AI innovations. So I think that will be very interesting and exciting at the same times. And then in this part, I will talk about some because AI is really already developed very fast in the last few years. We'll talk about some of our IGC's AI Plus action plan. So basically last year, through the dedicated phases of the development, we have through the three phases. It's a very long process. We have the overall coordination, detailed design, and summary and refinement. We have carried out a very good study to develop an overall and specialized planning report to cover off some key issues when the enterprise level to develop the AI. So we developed some, the business level application blueprint to talk about what are the key applications, and also which is more than 300 applications. And then we derive some really key scenarios from that to the task as a key scenario that we have to use AI, to show that they are powerful. And also we derive some important capabilities blueprint, and so to show that the AI should have some capabilities that can be useful in the power system. And now, based on that, we derive this SGC AI Plus plan. So to hope that we can using this 1+1, basically one overall report and 6 specialized report to cover the planning, asset management, and marketing side, grid operation, and also the system digitalization and the guidelines, to guide the system. So also we write one white book, powers AI Plus white book, to guide the company's overall AI development. So in this overall plan, so we derive and develop a general framework. We call it a 3-5-4-1 over plan. Basically, we want to using the very foundational key elements from the AI, that is the computing power, computing data, as well as the model. So model we consider two parts. One is the power, like the large model that is really popular right now, and also some smaller model and the specialized model. And then we have the platform. We have this platform, computing power, data model. These 4 key elements, to support the overall development of the system. And then within these models, especially, we'll cover the vision model, the language model, the multi-model model, as well as the scientific computing model, because for the operation side there's many computing tasks. And then these large models, they can coordinate it with more specialized and smaller models to support the different system, to support marketing, to support some asset management as well. And then with that, we have some technical capabilities, including we have the cognitive intelligence, we have the perceptual intelligence, decision intelligence, embedded intelligence, the robotics, and also have the AI for science, and which has a more promising field. And then with these 5 typical capabilities, we can support the business application, including the planning and construction, the grid operation, the equipment and asset management, the field operation, the customer service, as a general the company corporate management. But at the same time, we also need to understand that AI is not a single tool, so it has to be a supporting system. So there's a corresponding standard, corresponding the ecosystem, organization and some operation side to support. So this is basically the overall and general framework we are developing for our AI Plus plan. So we have actually, as mentioned, we have already developed more than 600 applications, and then we selected as more than 60 as a typical application scenarios. And to make a further step, we derive 8 key scenarios. And including, we have the from a plan distribution system diagnosis and planning to cover the planning and construction field. We have the simulation analysis and operation and distribution system forecasting and decision support for the grid operation. We have the main equipment state evaluation and maintenance for the asset management side. And also we have the customer service support for the customer field. And also we have the customer field operation, for to handle, these some substation field operation. And also for the corporate management side, we have this supply chain coordinated services and also some like digitalization and R&D and maintenance part. So one of the reason and the principle to derive these 8 scenarios is based on how frequent and how frequency high frequent of these scenarios, and also we want this like this topic and this field, these scenarios are be cross-disciplinary. And also we hope with AI, we can have the like big innovation and big improvement to improve the productivity of these original scenarios. And then we'll talk about this capability side. So we, as mentioned, we have this perceptual, like cognitive, decision, and embodied intelligence. So we want this capability, to be composable, scalable, as well as reusable, that to support overall deep integration of the AI technology and business. Like for example, for the perceptual intelligence part, this is mainly like they can hear, they can view, and they can handle this multi-model data. So that is very similar to the human. And then we have the cognitive, so this AI system, if they have the cognitive intelligence, they can do a better job in reasoning, they can evaluate, they can integrate with the knowledge as well. And for the decision, they can do a better job in the forecasting. They can do some analysis as a optimization. So because my personal background is from the grid operation side, so a lot of example probably I will use is from this decision intelligence part. And also we have embodied intelligence, which is a very hot topic in this year and last year, because this is a very typical example, like for the robotics, to how do we better do the human AI collaboration, and how do we do this autonomy as well. And the AI for science, actually, they are using these equation solving, like modeling and disaggregation and aggregation. Actually, they are collaborated with decision intelligence to support overall grid operation. So actually, so we know that large model is very popular last year. So for the SGC ourselves, we actually develop our Guangming Power large model system. We cover the vision model, we cover the multi-model model, we cover the language model, as well as some scientific model. And actually, some model are already developed, but some model are still under development. So right now, we are actually developing our scientific model and some larger multi-model model. And actually, some of the large model have already been used and adopted in the provincial systems in the SGCC. So right now, I'll try to cover some of the typical applications in SGCC. So here, we mentioned we have derived some key scenarios. So here we're using some example from the planning, construction, equipment management, grid operation, and customer service to show how AI can improve the overall productivities. So from this rough pictures, we can see that for example, for the grid operation, for the distribution side load transfer, the original planning time can reduced to 96% would be reduced. And also the important planning scheme time can reduce like 98%, which can see is a very dramatic change. And we can handle and the equipment management side from original 1 week to right now only 10 minutes. So the net diagnosis accuracy will be also like 85%. So one of the example I will try to mention is this planning and the construction. So that will be mainly focused on how do we better when we optimizing the main grid, how to strengthening the distribution grid at the same time to support the high quality development of the new energy. So with this AI project and achievement, actually we have developed like the intelligent distribution planning and grid diagnosis engine. So that's actually reduced the overall time required for a single diagnosis from the 20 days to 5 days. We can see that originally with human operation, like human engineers, the original design will be like in 20 days, but right now with AI, we can use 5 days to achieve this work. So we can, in addition, overall, the planning procedures will be from the more annual design, to the more online fashion. So there will be changing the overall mode from this qualitative to the quantitative mode. In this equipment management part, so actually we have also because in HCC we have more than 1.2 million kilometer transmission lines, which is a very large number. So we have even for the human like engineers, it's very hard, to inspect all these lines. So we established this 3D inspection plus the paranomic monitoring like model, to using this drone to help us do these like inspections. So we can annually inspect, more than 6.5 million towers, to help recognize the system like potential faults. And so annually, so we process 110 million pictures and to cover more than like 98% of the lines. And also we can achieve the accuracy of more than like 91%. And so we can have better understanding for the potential like fault and the hazard from the hour level to minute level. They will be significantly enhancing the efficiency and effectiveness of the power line maintenance. And from the grid operation, so I will using the example for this load transfer, especially from the distribution side. So actually, the original load transfer scheme will exceed, with this adoption of the AI, will reduce from the 30 minutes to 1 minute for a single decision time. So we can see that is a very significant improvement. And before some really important plan, the preparation scheme will reduce from 10 hours to 10 minutes. So this will actually drive, the transformation for the different network from the traditional more manual operation side to a more automatic and intelligence simulations. So in addition, so we have the customer service because, as the utility company, so we have a lot of customers. So for the SGC, we have 1.1 billion electricity customer, which is a large number. So we have using, the AI techniques to help us, to derive some like manual operation of the power supply scheme. So right now with this AI tool, the accuracy rate for scheme inference can exceed 99%, so which is very good. And the average time required to prepare the scheme has been reduced from 7 days to 1 day. So overall speaking, so we can also using the more visualized ways to help the customer and to improve the overall customer experience and to make sure they're satisfied with our electricity services. So those are some like applications right now. So in this topic, we'll also cover some of the projections, we're thinking important for the AI for science in the power system operation part. So in power systems, there are actually a lot of computational tasks that are more based on the mathematical models. So we have the differential like algebraic equations to solve. So we also have some optimization tasks as well as some like time series forecasting jobs. So including like, for example, for the algebraic equation, we have the power flow, we have the say estimation, and for the differential equations, we have some transient simulations. Also, we have, this more general like multi-energy analysis to coordinate between the, the electricities with the gas system and the heating system as well. Also, we have a lot of optimization, no matter it's convex or non-convex. We have economic dispatch, which is a linear program. And also we have the more unit commitment, which is like the mixed integer linear program. So they are directly related to the market clearing to relate to the electricity market. And also we have the optimal power flow, which is also help determine the like the generation dispatch in a network. And also for the planning, we have this generation capacity planning as well as the transmission capacity planning. All the also the like the optimization tasks to help you guide what the system is planning to develop for. And also we have, mentioned the time series forecasting. We have the load forecasting, renewable wind, solar forecasting, as well as when you have considered the market, you have this like price forecasting as well. So here, for us, we think about this AI for science is basically integrate these physics equations, integrate the deep neural networks and expert knowledge to achieve the fusion between the like physical mechanism, the data, as well as the knowledge. So, and there has a very common like scientific task we want to achieve. One is we call it like a positive problem. Basically, when we have the equations, when we have know the like classic mechanism, how do we arrive and derive and solve this problem faster? So basically, this is a positive problems. from the equation to system state. At the same time, it's very common in the power system that we have the very good measurement. We have some like to understand some of the states. So we want to infer and what is the system equations, what is the model. So basically the inverse problem, like we have the generation modeling, the like load modeling part. So basically those like this equation, positive problem and inverse problem are the important task, as well as we also have other like generalization, task disaggregation and aggregation. We want to use all these, problems to lastly, use AI, to base this knowledge, based on this mechanism to discover the new knowledge. This is the ultimate and very not ultimate, and I mean it's very important, like goal we want to AI to achieve us for, like to discover some new knowledge. So from our perspective, AI for science in the power system paradigm should include the physical equations, include the mathematical methods, including the knowledge as well as some like logical deductions. So we have recently, like we know that AI is developing fast, especially with its own large language model, ChatGPT, like Cloudy, they are really powerful. So one of the basic, very important tasks or the like technique behind that is the foundation models. And for example, one is like this transformer structure, and also I think because they can using this transformer to learn and capture the system sequential features quite well. But also at the same time, there's another very interesting and very good neural network, which is a graph neural network. Basically, the system is embedded in this, like their graph is topology is naturally embedded in this neural network. So that is also very interesting because we know that the power system or energy system actually is a physical network. So with this physical network, so actually they are naturally aligned with this graph neural network scheme and concepts. So that using this graph neural network, say some of the features like between the nodes, between the edges, between the lines can be effectively captured. So with this transformer structure and with this GN graph neural network structures, like we can do some better downstream jobs, including the time series forecasting, simulation analysis, and optimization. So we have some application to extract structure features and to handle using these models to generate some scenario for this information scarce case, to help us, to boost and to handle some extreme operating condition data set. And also we're using some graph computation to accelerate the power flow and computation. And also we're using combine this transformer gene informed neural network, with a pre-trained model, to better like solve the system like power flow equations estimation and achieve very good accuracy. And also some examples that I mentioned before is more from the positive problem side, but for the inverse problem, we can integrate some deep reinforcement learning operators, to learn from the system models and to have a good accuracy to learn the generator model, load model, and network model parameters. Also, we have this like great optimization, to combine the AI with classic solvers, to achieve the rapid computation for the overall system dispatch and to support the system operations. So they have different like alignment and AI optimization like structures. They have in the series connected architecture. They can have these like iterative architectures. So we combine these things, we can improve the overall computation like performance. Especially we know that the solver side that's very accurate, but they may have these like computational bottlenecks. The AI is very fast, but maybe their accuracy is not enough. So with combining these strengths, we hope to achieve the good benefits and from the both sides. So we also use some examples to achieve some really good results. So basically, we have examples to hope to develop this overall framework to leverage the AI and this large language model and these large models to achieve some really good AI for science application in the power system. So in general, we believe with this Guangming large power model, the large model developed from our company, so we can have like build an AI architecture centered on this and to deepen the large-scale application of the high-value, high-frequency routine business, and to promote the application and exploration for the cutting-edge directions, and to comprehensively empower the construction of the new power system and promote the high-quality development of the enterprise. So right now, we know that we already have the very good physical grid, and we are trying to build this digital grid. But we have different techniques, and these techniques has to be combined together. For example, we have this AI for science examples we have mentioned before, but AI for science can be understand as an example from the direction of the internal understanding, to handle understanding what is the mechanisms in this digital grid. And in the future, we also have this embodied intelligence as an external cognition side to show maybe we can do better in another direction. So both these internal and external directions can be combined together to improve overall both the physical grid and the digital grid as well. So one of the conclusions is that with this AI, we believe this power system is evolving into this cyber-physical social system. So it is very high dimensionality with high complexity and strong linearities. So the AI for science and AI, their perspective can provide very good like a paradigm shift in the overall systems. At the same time, we have to understand that power system is a really conservative system, that we cannot suffer the big impact from the outages. So we have to use AI to ensure that system and this model is trustworthy enough. So that are very important tasks to be handled, and that is the topic for today. Yeah, thank you.
Thank you very much, Dr. Yishen. This was very, very interesting presentation, and I'm impressed by the way you use on a very global and very rational and accurate way IA within the power system. This is very impressive.
Thank you very much for the Marilyn, and thank you very much for this WFEO for the opportunities. I'm really happy to join the seminar and introduce some of the work. Yeah, thank you very much. Yeah.
Thank you very much. Bye.
Yeah, bye. Have a great day. Yeah.